So for example number 4 out of your textbook, we're still dealing with exponential and logistic modeling. We like those mathematical models because they really represent like growth or decay in populations. So we use them for populations all the time. So for example number 4, we're going to do radioactive decay. And so I'll just write this out. It says, suppose, now remember, whatever I write down on the board, I'd like for you guys to write down. Suppose the half-life of a radioactive substance, and we won't name it, we'll just call it some radioactive substance. Is 20 days. Radioactive substance is 20 days. Okay? Then it goes on to say I'm going to word it a little differently so you don't have to write down every word that's in the textbook. Your initial quantity is 5 grams. Okay. And then lastly it says how long until you have 1 gram. I suppose I should probably make that a different color, right? So how long until we have 1 gram? And so now, Mr. Adams, just so you guys aren't getting carpal tunnel from taking notes in my math class, I changed some of the wording of what the textbook says. So let me just say it out loud so we get a good grasp. You start off with 5 grams of a radioactive substance. Now, radioactive means that it's unstable. That means that some of it decays and literally becomes less than what it was. Okay? So you start with 5 grams. It has a half-life of 20 days. How long will it be until you get down to 1 day? Or 1 gram, right? So I said that wrong. So let me say it again so you guys aren't confused. We start with 5 grams. This is a radioactive substance that decays. How long will it be till you're left with 1 gram? And the only other thing they tell us is that the half-life is 20 days. Well, the way that we do this is we're going to think about, it's a radioactive decay, so it's a decay model, and we said exponentials are great for this because it decays a certain amount every time. Okay? And so what we know is, first let's start with the model. So the amount of substance we have, and we'll just use P of T, is equal to the initial amount you start off with, some sort of rate of change, right? Some sort of rate of change or a base, and then usually it's multiplied by a time, a unit of time. Okay? All right, so we want an equation that sort of looks like this. Well, we know a couple of things. One thing we know is, we know that our initial quantity P naught is equal to 5 grams. We know that the base is what we multiply it by. What do we multiply it by if we're talking about a half-life? 0.5 or 1/2, right? So we know that our rate of change is 1/2. Okay. Time is really the question that they're asking us, right? Time is really what they're asking us. Okay? So, and I know the final amount. What should the final amount be? Yeah, so I'm going to do this just a little different than the way the textbook is because I think my way is easier. Okay? So now watch this. The final amount should be 1 gram. Okay? Only thing that bugs me about this is I'm a little troubled by the time. If I just leave that as t, what does that make that? That's the unit of time. And we're basing the unit of time on how many days? 20 days. Right? So if I go through and I crank through this thing and I get some value for t, that t represents how many 20-day units. Is there an easy way to set up this equation where I don't have to make the conversion from, like, in other words, if I solve this thing and I get like 1.5, like t equals 1.5, that 1.5 represents 1.5 times 20 days. Is there something I could do in the beginning of my equation that'll help out? Well, if we wanted to make it per day, what we could do is we could change this like this. We would say out of 20. So that way, if I get 20 out of 20, that's 1 cycle. If I get 10 out of 20, that's half a cycle. And so normally, and I'll show you a more general form in another example, but normally what we would do is we would change that unit of time into, in other words, if we said, if we were told in years and we wanted to know how many days, I would say t divided by 365, stuff like that. Okay. All right. So that's what we're going to do. So now let's plug this in and chug along. Okay. So all right, that's what I wanted to do. So I'm going to scroll this down a little bit, and we're going to plug in our numbers and see what we get. So I'm going to say 1 gram is equal to 5 grams times the quantity 1/2 raised to the t over 20. Okay, so far we're doing so good. How do I get that t out of there? I got to solve for t, and so I got a real problem with that t. Think about that. We'll come back to that in a second. All right, so now here's the thing. Let's try to get a bunch of stuff away from the t first, and then we'll deal with the t when we get to it, okay? So I could get rid of this 5 grams by dividing both sides by 5 grams. And technically, I shouldn't put GM. Technically, the unit for gram, or the abbreviation, is just M. Or not M, but just G. I don't know why I wrote down GM. Sometimes students do that. I don't know where they get it from. So anyways, the 5 grams cancels out with 5 grams, and grams cancels out with grams. So now we have like a unitless number, 1/5. So on the next line, we have 1/5 is equal to 1/2 raised to the t. So I have 1 over 5 is equal to 1/2 raised to the this. So the issue here is that there's no easy way to get rid of, to bring that t down from being a power. Well, there is. Does anybody remember how we do it? We did this is the last section or chapter. Let me start another screen. See, one of the cool things about the property of logs, I can take any logarithmic function, okay? So, for example, if I say the log of x squared, there's a property of logs that will let me, that's equal to, it will allow me to take this 2 and toss it to the front. So that's equal to 2 the natural log of x. And that'll work with any log. So if I were to do log base 3.14 of x squared, I could rewrite that as 2 log 3.14 of x. Okay? So I don't know if you guys remember this or not. I noticed as I was writing it down, some of you guys were amazed. So make sure you write this down, because this is a property we're going to use a lot in this class. Okay? In fact, in calculus, we're going over this now, and we use this a ton in calculus. And so we're going to try to apply this property to pull that t over 20 out of the power, out of the exponent, and bring it down to the front, and then we can just solve for t algebraically. Okay? Now, we like to use the natural log because the natural log, we have a key for that on our calculator. Okay? And because we have a key for that on our calculator, we'll use the natural log. So what I'm going to do is I'm going to say, all right, let's take the natural log of both sides. So I'm going to say the natural log of 1/5, and then over here I'm going to say the natural log of 1/2 raised to the t over 20. Right? So just like everything else we've learned in algebra, whatever you do to one side, you have to do to the other side. Now we did that because what we really want to do is we want to take this and we want to toss it to the front. In other words, we're going to say the natural log of 1/5 is equal to t times the natural log, or it's actually t over 20 times the natural log of 1/2. Does that make sense? Now what I could do is I want to start getting t by itself, so what I'm going to do is I can move this natural log over. So I'm going to say, I'm going to divide both sides by the natural log of 1/2. Okay? Now when I do that, this will cancel, and I'm left with the natural log of 1/2, or 1/5, divided by the natural log of 1/2 is equal to t over 20. What do I do next? What do I do next? Multiply by 20. I play these videos that we do in class here. So we're going to multiply both sides by 20. And my other pre-calculus class is at it's 7th hour, and this is 1st hour, right? So they're like, what is taking them so long to answer? They don't know that you guys aren't awake yet. It's really funny. All right, so now the natural log of 1/5, it looks kind of funny, but that's actually a number, right? And the natural log of 1/2, it looks kind of funny, but that's actually a number. So it's 20 times a number divided by another number. That makes sense? So now let's just, let's do it. Let's plug it in the calculator and see what that is. So I'm going to say 20 times the natural log of 1 divided by 5 divided by the natural log of 1 divided by 2, right? Is that what it was? And hit enter. And we get 46.43. So 46.43 is approximately what t is. So what did I just do? Somebody tell me what t is approximately 46.43 means. Yeah, go ahead. I'm not going to call your name because we're recording, but yeah.
That's how many days it's going to take for you to get to 1 gram.
Yep. So this is how many days it's going to take. So we start off with 5 grams of this radioactive substance. After 46.43 days, we're going to be left with 1 gram. And we could common sense double check that, right? After 20 days, my 5 grams goes down to 2.5, right? Because it's 1/2 every 20 days. After another 20 days, my 2.5 grams goes down to 1.25, right? So let's write like a little chart. So if we wanted to do like a common sense check, see if our answer makes sense. Because you know Mr. Adams is really smart, but I could have hit the wrong button on my calculator. So if I make a little chart, after 20 days, okay, so on the first day, day 0, I have 5 grams. After 20 days, I'm left with 1/2 of that, which is 2.5. After another 20 days, which is 40 days from the beginning, I'm left with 1/2 of 2.5, which is 1.25. And then if I were to go another 60 days, it would be 1/2 of that. 46 seems like a reasonable answer to be at 1 gram, doesn't it? That seems reasonable. If I had 460, that'd be crazy, right? So now how do I verify that to make sure it's the right answer? Anybody have an idea? Well, we said what we're left with should be the initial amount, which is 5 grams, times the rate, which is 1/2, raised to the t over 20. So probably if I plug in 46.43 in my calculator into this equation, I should get what for an answer? 1 gram, right? So what I'm going to do is, let's do that. So I'm going to say 5 times, in parentheses, 1 divided by 2, close parentheses, raised to the, start parentheses, and I'm going to put 46 point, and I'm going to write the whole thing out. 385, actually if we round that off, it should have been 0.44, not 0.43. 5619 divided by 20. So when I hit enter, what should I get? Or really close to. Remember, we're rounding and using decimals, so it might not come up exactly 1. So it might be close to 1 though. Let's see. 1.001. That's pretty good. Does that make sense? Now, when I hit that, I saw a couple people, they kind of made like a look. Do we make this look on our face because it wasn't exactly 1? Or is that just the look you make? I'm thinking it hurts. No, the reason it's not exactly 1 is because we rounded the decimals. This decimal probably goes on a little further. Your calculator just truncates it. Okay? That's it. Any questions?